Okay, welcome to another Stat 432 video. We have some starter code, I have some notes, so let's talk about logistic regression in R. This will be one of two videos talking about R concepts for this week, if you're following along and watching the videos that way. So we're mostly going to talk specifically about logistic regression in this video, and then the next video we'll talk about binary classification, but in some sense, we're going to introduce some binary classification ideas in this video alongside logistic regression. So they'll kind of be videos that really need to go together. Okay, so for this particular video, we don't need a lot of packages. We almost don't need any, but we're going to use a couple to make our lives easier. That is the Tibble package, so I can make the data into Tibbles just so it prints nicer. And then the ML bench package, just so I can simulate some data quickly so we can try some things out. But before we actually use the ML bench package, I'm going to simulate some data myself. This code, all this code will be available to you in the book website somewhere, depending on how you're looking at this. But this code isn't super important at the moment, but I do think it's not too hard to understand. But we're just going to kind of use it, and I have it here for simplicity. Okay, so I'm going to use that function to simulate some data. And let's have a look at that. So here's what we have. Very simple data frame here. One feature X, one response Y. And notice that the response Y is a factor variable. So we're going to play around with that a little bit. And notice that the two possible levels of the factor variable are 0 and 1. I can show that a little more explicitly. There we go. And notice that 0 is the first level and 1 is the second level. When we start using logistic regression, we're going to find that whatever is the first level, it could be, say cat and dog for the two levels. So if cat was the first level, that would correspond to 0 mathematically. And if dog is the second level, that would be 1 mathematically. So it's always important to check the levels of the response variable and see which one comes first, which is 0, and see which one comes second, which is going to be 1. Okay, I'm also going to simulate the data in a different way. You'll notice that it's the same data, except y is now an integer value, or we can just simply think of that as numeric. So that'll be important. Okay, so I'm going to make a plot here, which you can't see because of my face. So let's get rid of that, or maybe just move me up here. Okay. All right. So let's make this a bit bigger. Maybe let's do. Okay. I hate that this scroll bar is here, but oh well. I don't think we're gonna get rid of that. Okay. Anyway, let's move me a little bit. Oh gosh, didn't want to do that. Let's do this. Okay. So what we have here, so this Y label is a little confusing yet because this isn't true yet, but what we have here is a plot of our data. And the x-axis is the feature X, and the y-axis, even though it says estimated probability, that's what we're going to put on the plot eventually. It shows, some of the data has value 0, some of the data has value 1. Okay. And again, technically it could be, cat, dog, pass, fail, whatever, but mathematically we're internally thinking of it in 0s and 1s. So before I even get to linear regression, I want to try using, before I get to logistic regression, I want to try just ordinary linear regression. So this expression here sort of hints that it's not actually a terrible thing to do, right? Because ultimately, what linear regression is interested in is the expected value of y given x. Well, when y can only take two values, and we complete this expectation, that's 1 times the probability that y is 1 given x, plus 0 times the probability that y is, this should say, 0 given x is x. Well, that's exactly the probability that y is 1 given x is x, which is kind of what we want in binary classification. So let's try that. So I'm going to call this fit. Let's call it, I wrote fit for some reason in my notes. I'm going to stick with it. I like mod better generally, though. Fit lm equals lm y tilde x data is, what do we call it? Sim data numeric, because I can't use a factor variable inside of lm for the response. That wouldn't work. Okay, so let's do that. And here are our estimated coefficients. Here's our beta 0 hat, and here's our beta 1 hat. Something I want to make note of right off the bat. Let's say I change this a little bit. Oops, like this. And instead of LM, let's say I use GLM. That's interesting. This estimated coefficient, exactly the same as this. This estimated coefficient, exactly the same as this. Interesting. So it kind of doesn't matter which one we use. But so what I'm trying to get across here is that the GLM function, which we're about to use for logistic regression, actually does a lot more than that if it's generalized linear models. And one of those models in particular is just the linear model, basically with an identity link function, but we don't need to get into that. But notice that by default, if y is numeric and we use GLM, it's doing linear regression. So that's something to keep in mind. Okay, so now let's move into using logistic regression. So I'm going to call this fit GLM, and I'm going to do GLM y tilde x. Well, you know what? Why don't I just copy paste a little bit? Okay, except clearly, this is not logistic regression. This is linear regression. So what do we have to do to make it logistic regression? Well, we need to introduce a link function. And we're going to use what's called the binomial link function. Except that doesn't work. Except because link is not the name of the argument. It's actually family. Okay. There we go. Does that work? Okay, so that works, and I wish it didn't. But so that fits logistic regression. But what I want to say is we should be using the data with a factor variable there. And when we do that, we get the same thing. But what I want to note is that if this will error if I do it the right way, right? So if I try to do, so notice if I try to put this here, this here, it won't work because it doesn't like the factor thing. So will GLM complain if the response isn't a factor? No, but you still should do it. Although here it doesn't make a huge difference. But it's a good habit to get into, and we'll see some examples of that later. But something I want to note is that this might look a little funny, this saying family equals binomial. Because if I type binomial down here, if I can spell, we notice that it's a function. So I'm supplying a function here, and that function actually has arguments of its own, in particular a link. And the link is called logit. So if we pull up the notes we were looking at here, so here we sort of see this somewhere here. Yeah, so here we're sort of talking about this notion of the logit link. So technically, by default, when you say binomial here, that it tells it to use a logit link, but just note that you could actually change that. For example, you can make this probit, and it would do something slightly different, but ultimately accomplishing the same goal. But that's just a note that these two things do the same thing. Maybe we'll verify that. Okay, so that gets estimated coefficients like negative 1.4 and 6.3. Okay, so it's the same thing. Okay, so just a note there. Okay, so what I want to notice real quick before I plot something is that if I do predict of fit underscore lm, so notice that it returns numbers. And that's sort of what we would expect from a linear model. You might already notice something about these numbers that we don't like. What happens if we do predict fit GLM? Well, it returns some numbers, but notice these numbers are sort of clearly not probabilities, right? You can't have a probability of negative 9.199, right? That's just absurd. So So if we do type equals link, that's the default, and that's what we get back here. Whereas if instead we did type equals response, these numbers look more like what we want. These look like probabilities. And I think that was sort of indicated in the notes at the end here. So if you do type equals response, it gets you the estimated probabilities. If you do type equals link, that gets you, what do we have here? An estimate of the linear combination of the features. So that's just something to keep in mind. And then later we'll sort of utilize the fact that a probability of 0.5, estimated or otherwise, is equivalent to a link of 0, estimated or not, depending on what we're talking about. Okay. So now I'm going to plot some things. Okay, so that's just recreating the plot we already had. So now what I'm going to do is add the fitted linear model. And hopefully right away you see some problems. So what this is supposed to be is, say, for an x value of 0, this tells us that there's an estimated probability that y is 1 of something like a little under 0.4. At an x value of 1, we come up here. We have an estimated probability that y is 1 of a little under 0.8, right? But there's a huge obvious problem with this, which is that these would then indicate negative probabilities, and we don't like that. So what this code does is it will take the logistic regression and add the estimated probability that y is 1 for each x. And notice something in this dashed blue line here. Well, it's always between 0 and 1. And notably, it's pretty close to 0 when there's only observations of 0. It's pretty close to 1 when there's only observations of 1. And it makes this sort of S shape where there's a little bit of, you can't separate the data. There's some 1s and some 0s. So that's pretty good. I should probably add the legend that I did. Okay, so that's using these two models to get the predicted probabilities. But what if we wanted to make classifications? Well, so this line is for a probability of 0.5. So what this says is, I'm just going to add these, and I'm not necessarily going to say how I did it. So for the logistic regression, I found the x value where the 0.5 intersects with the predicted probabilities. So what this means is that any x value bigger than whatever this is, like 0.25, so anything over here, we would classify to 1. So in the training data, we would get this one incorrect, I guess. And anything over here, we would classify to 0. So we would get this one wrong and this one wrong in the training data set, because we would be classifying this as 0. And we could do the same thing with the regular old regression. And we see that it doesn't do too bad, right? So we find where they intersect. So this x value here, it's pretty similar actually. But anything to the right of it, we classify to 1. So we're getting all these correct. And anything to the left of it, we would classify to 0. So we're getting these 3 wrong. So moral of the story is, can you use linear regression to make classifications? Yeah. Is it a good idea? Maybe not. Why not just use logistic regression? It'll get you fairly similar classifications, at least in this example. I don't guarantee that all the time. But the estimated probabilities will make sense. And sometimes that's more important than the classifications themselves. So if you're doing classification, use a classification technique. In this case, logistic regression. Okay, cool. I need a pen. I want to check my notes off as I go to make sure I don't forget anything. So we're about here. Okay, perfect. All right, so moving on. So now I want to look at two-dimensional data. I actually think that this plot that we're looking at right now is sometimes a little hard to understand because it's only one feature variable. Okay, so I'm going to simulate some data using the ML bench package. It looks like this. So now we have two feature variables, x1 and x2. And this classes variable is going to be the response. Notice that it is factor. It has two levels, 1 and 2. And notice that they are ordered, so 1 comes first, 2 comes second. So when we do logistic regression, the level of 1 is mathematically going to be 0 under the hood, and the level 2 is going to be 1 under the hood. Confusing, but good to know. Okay, so one thing you should often do when you're considering binary classification, which we are now, is check the what we call balance of the data. So there's 44 ones, 56 twos. That's pretty close to 50-50. There's just a little more too, but so that's not a big deal. Okay, so I'm going to plot the data. The code used to plot this is not super important, but we see here the two classes. And again, black is 1, red is 2. I really got to start adding legends for that. Okay, so again, so these are the ones up here, and it's kind of a blob of data, for lack of a better technical term. And there's this red blob down here. These are the twos. And we see that, like, there's a little bit of overlap between the two. So we're probably not going to get perfect classification. So this is a little trick that I'm going to do to make a graphic. It's not super important that you know how to do this, but so what I have here is a sequence of potential x1 values, right? So these are all the potential x1 values that I'm going to predict at. And then here are a bunch of x2 values that I'm going to predict at. So what this expand grid function does, which is pretty nice, and we'll just look at some of that output, it sort of creates a grid of all, basically it does like a cross of all those possible things. So for a fixed x2 value of -3.5, we consider all of the x1 values. For then x2 of -3.4, we consider all of the x1 values, and so on and so forth. Okay, so now I want to fit a model. I'm calling it bad. I almost forget why I'm doing that. No, it's not a bad model. This is going to be a perfectly fine model. That's for something later, and I did a bad copy-paste job. Okay, so I'm going to call this model. Am I on the right page? Yeah, okay. So we want to fit a logistic regression. So classes is the response. We'll use the two features. So the data is this training data for the blob data. I simulated some, and I'm calling it a training data. I simulated some more. I'm calling it a test data. Obviously, you wouldn't be able to do this in practice, but we're sort of exploring linear regression. We're not really using it. That'll be for the next video, sort of. Okay, and I need to specify family equals binomial. Okay, let's just have a check here. Okay, cool. So what I'm going to do now is for each of the points in this XY vals, I want to make a classification from the logistic regression model I just did. So let's have a look. So I'm going to do predict with the mod I just fit, and I'm going to predict on this data here. Okay, cool. So remember, these are not predicted probabilities. These are the estimated sum of the linear combination. So if I say, well, if these are greater than 0, predict it to be 2, the second class. If not, predict it to be 1. That will be what I want. I'm going to... Oh, sorry. Sorry. So this is true if this condition is met. That is, the estimated linear combination of predictors is greater than 0. Actually, let's do this the other way first. I'm going to show both. But so let's do type equals response. And I need close paren, right? So these are probabilities that y is 1, which is actually 2 in this case. So if I say bigger than 0.5, well, so when it's true here, that means we should classify to red or 2. And if not, we should classify to 1 or the black points. So I'm going to do if else. So what did I say? Should be red, and if not, black. Except those should be 1s and 2s. But I'm using colors. And for the sake of the plot that I'm about to make, I'm going to make this light pink. And I'm going to make this light gray. So, but again, gray, black, that's these points over here, or that class. light pink, red, that's these points over here. So if the predicted probability that y is the second class, the reds, make it light pink, if not light gray. Okay, so that's that. So I'm going to call this pred underscore xy. But I want to note that this would be the same as if we did this. So instead of type is response, we do type is link, which is the default, and only compare to 0. Right, except I'm going to do this temporarily just to prove my point. So run that, and then we'll do all.equal this, comma, this. So hopefully you believe me. Okay, moving on. So what I'm about to do is a bit of a hack to make a plot, but we'll do it anyway. Okay, apparently I wanted to write this code in front of you. So x2, well no, I can steal this to start. No, I can't. Okay, so what I want to do is this. x.1, comma data equals xy vals, right? What does that look like? Okay, so that just looks like a big black mass, right? So that's just plotting a point at each of those places I said. But now what I'm going to do is color them according to the predictions I made here. Okay, that's cool. You might notice something about that. And then just so my plot looks a little bit nicer, I'm going to do x is between -3 and 3, and y is between, let's see, -3 and 3. How's that look? Okay, that's better. So you can see that it's kind of a hack for coloring the background according to what we're going to classify to. If you really see, it's kind of like low resolution and there's some gaps in between, but good enough. Can I clean this up at all? Yes. If I did a different plotting character, squares instead of empty circles, that'll sort of make that look a little bit better. Okay, so then what I'm going to do is I'm going to put the original data back. So that looks something like, I can just steal this now. Right, is that what I did? Yes, okay. Okay, so this picture is decent. Are there other ways to do this? Yes, so the plotting code I'm using is not super important here. But so basically anywhere that there's a light gray background, the logistic regression model that we fit there would classify to the first class or the black points here. And anywhere that the background is light pink, well, that would classify to the second class, that is the 2 or red. So, oh. Okay, so this is exactly that code. I don't know what I was doing here. But so with a little bit of math, that is, if we look at exactly here, so we can analytically solve for this right here in the predicted sense. So if we do that, that's this little bit of math I have, right, which again is equivalent to this. So basically, I need to, so in this example here, we had 4 plus 2x1 minus 2x2, set that equal to 0 and solve. We have different coefficients here. They look like this, but if we solve that same thing, we can get a line, which is called the decision boundary. So by my math, okay, so let's just, that's the same plot already. But so what I need to do is add a line. And so the intercept of that is minus the coefficient. Well, here, real quick. Before we do that, let's do this. So notice that we have the 3 coefficient values for the intercept, x1 and x2. So intercept, x1, x2. So I believe if we do minus the intercept divided by beta 2 hat, and then for the slope, it would be minus this coefficient divided by this coefficient. I need a comma here. And again, that's just the math that I did here previously. And then what I want to do here, I want to make this a really thick line. So I sort of, what I'm going to do is I'm going to get rid of this jaggedness here with a really thick line. And then let's make it white, just because that looks like it'll contrast really well. Did I do this correctly? Moment of truth. Hey, I did it. So there's the decision boundary. And again, the decision boundary is the set of x1, x2 such that the prediction probability is 0.5, or the sum of the linear combination is 0. Same thing. So that's pretty cool. Okay. So far we have this notion that logistic regression is a sort of form of linear model, and it makes linear decision boundaries. But is that always the case? So now, while I'm here, sorry, not yet. I spoke too soon. I want to calculate the test misclassification real quick. So let's do that. So I needed to make predictions with my model on the test data. What do we call that? Blob test. What a name. Okay. Okay, and remember these are the estimated linear combination there. So let's look at these bigger than 0. So when that's the case, we should return 2. So we'll do an if else. So if that condition is true, return 2. If not, return 1. That looks pretty good, except I should make it a factor. I don't think I needed to make them characters, but it's all the same. One thing you should always check is when you make that factor variable after all the predictions is that the levels are both the same and in the same order. And if we look at blob test $ classes, we see the same thing here. Okay, so that's good. So I'll call this pred. So those are my predictions on the test set. So now what I want to do is I want to compare blob underscore test $ classes. I want to see when it's not equal to the predictions, and I want to average that result. So this is my test misclassification. So about 7% error on average. Not terrible. And that's based on this plot we're looking at. I always point as if you can see where I'm pointing. I need to use my mouse. So, you know, we see in the training data, we see errors here, and we can sort of intuit how that would generalize, so that's pretty good. Okay, so now what I was talking about, this notion that, well, so far a logistic regression is a linear model, therefore it gives linear decision boundaries. Except no. Much like with ordinary linear regression, if we add the right transformations of our features, we can get sort of like non-linear things. We can get non-linear decision boundaries in sort of the same way here. So let's do that. Okay. So I have some data here. I'm going to simulate a tiny or a relatively small training set and then also a test set. So again, we have x1 and x2, two feature variables, classes, the response, it's a factor, same two levels, 1 and 2, 1 first, 2 second. Although you could flip that, but that'd be silly. Once again, the data is fairly balanced. We could do a nice little trick here if we wanted to see the proportions in those, because this time there's not 100 observations, so it's not easy to see. So 52% of the trained data is the second class. Okay, cool. So let's plot this data. So here we see something very different. So the one class, the first class, relates to the black points here, and that's sort of this circle-ish thing on the inside. I guess it would look more like a circle if I sort of made it a square plot. Let's do that real quick. So you sort of see this internal circle here. That's why I called it circle data. And then outside of it, in this sort of region between -1 and 1, this square, excuse me, the rest of the points are for class 2, which are, in this case, red. Okay. So this is just that similar trick I did last time, because I'm going to predict at just a bunch of grid points and color it accordingly. Okay. So this time, I first want to fit a bad plot, and then I will fit a good plot. So that's why I had those notes to myself. Okay. So first, I'm going to sort of just go on autopilot. So I'm going to say mod bad, and I'm really spoiling what's going to happen here. So we'll say classes tilde da, da, da. So we're going to use both predictors. Data is the circle train data, and family is binomial. I think that's right. So then I want to predict, we'll call it bad XY. So I'm making predictions on this. So I'm going to predict with the bad model on the on these points here, and then if that's bigger than 0, I'm gonna make it light pink. So we're gonna do if else that will do that light pink, which is the second class, which is y equals 1 mathematically. Then this will be light gray, like that. I seem to have... No, that's good, right? Let's just check that real quick before I do it. Okay, that seems good. All right, so now I want to put those points on a plot. So what I'm going to do is I'm going to kind of steal this to see if that makes my life easier, right? But instead of this data, I want to do this data, and the colors are going to be from here. And I think 15 is a square, which sort of works out well here. Aha, perfect. And then we'll just do quickly, x will go between -1 and 1. I don't know why I didn't just leave this code here. And then y lim is -1, 1. This is just cosmetic. And then we need to put the points in. So the points will be exactly what we have here. Okay, and I think it's clear to anyone, this ain't doing too good. No, not too good at all, right? Trying to make a linear decision boundary discriminate a circle from all these points is pretty much not possible. And let's check the accuracy on that real quick, right? So if I do predict with my bad model on the test data, we get something like this. We'll do greater than 1 is when we classify to that second class. Otherwise, 1. I keep forgetting to type the if else before I do that. I'm kind of on autopilot here. Is that correct? Could not find if, okay, if else. Perfect. Let's make it a factor. And I think I want to call this something like pred bad. You see a pattern? Okay, and then let's check circle test classes. So that's the true response. So we're calculating test accuracy here. So when are those equal to the predictions? Okay, bunch of true falses. Wow, that's kind of garbage, right? So we're only correct 44% of the time. I might hint back here to say, well, we could have done better if we probably would have done better if we just classified everything to 2. Yeah? I mean, we can even do that real quick. So, yeah, so we did better with that. So this is a garbage model that we've created here. So let's make it good. How are we gonna do that? So turns out we can add transformations just like we could in a linear model, which hopefully you've seen before. So what I'm gonna do is I'm gonna add a quadratic term for x1 and x2 and the interaction between x1 and x2. So I wanna do, let's do poly x dot 1 degree 2 plus poly x dot 2 degree 2 plus x dot 1 colon x dot 2 for the interaction. And the data is, well, I can just kind of steal this now. Ooh, that line length is a little long, so let's do that. Okay, cool. Right, and I can kind of just steal some of my own code. So this will just get called good now, and we should do the predictions on the good model, so that's all the same. So let's do that. Oh, this is good. So when you're fitting logistic regression, you might see this sometimes. So this happens in one of two situations. One is when you can sort of perfectly separate your data, or 2, if you sort of get really close to it. Basically, it's numeric issues. But to be clear, this is a warning, not an error. So your model still fit. It's just being like, hey, maybe have a look. So the thing you'll notice is that these are truly wild coefficient values, and that's what's happening there. So basically, there's multiple possible coefficient values here that would sort of solve an equation here and get a separable thing. So you should not do inference. You should not believe the p-values related to these for the test, but we can still make predictions. So that's what we're going to do. So we already did that here on each of the x, y points. I mean, again, light pink is for 2, light gray is for 1. So we can make this plot here. And I need to change this to good. Otherwise, I think everything is in order. Aha! That's pretty cool. So just to make it a little more square, so the inside becomes a circle, logistic regression managed to learn a circle. It's not quite perfect, although this is kind of low resolution based on, the grids that I did. So this is not necessarily, you could solve for this circle if you wanted to. I just didn't feel like it. So this is my lazy hack to do that. I can't tell. I don't know if we're classifying these correctly or not. We could check. But anyway, whether or not it's perfect on the training data is irrelevant because we want to go to the test data and see how we did. But we can see that we've essentially learned a circle, even though this is a quote unquote linear model. But right. So let's check the performance real fast. So again, I'm going to sort of steal some code. So we'll call these the good predictions, and that's based on the good model. And now instead of light pink, we're doing 2 because that's what it actually is. Instead of light gray, we're doing 1 because again, that's what it actually is. And then I need to change this to this, and we would expect this to be really high, and it is almost 98%. And that kind of makes sense based on this picture we're looking at. Okay, so bottom line, to do logistic regression, use GLM. You put the response variable on the left of the tilde. You put your features on the right side. You say you're using the features and response from some data frame, and you say family equals binomial. The other thing you have to look out for is if we'll call this mod. And again, this is not real code, so this isn't going to run. When you say predict mod and then some other data, let's say, what this does is it only focuses on quote unquote y equals 1, right? So whatever the second level is in the factor variable that is the response. So this will output the estimate of eta here, whereas if we instead do comma type equals response, that will output an estimate of, where is it? Aha, here. The probability that y is 1 when x is x. So kind of a lot just to say that, but this is the main takeaway here. So we talked about logistic regression. We've kind of hinted at some things about binary classification. Because this video is already super long, I'm going to cut it here. And then in the next video, we'll talk specifically about binary classification, but not only as it relates to logistic regression. We can use any classifier we want, but we'll evaluate it as a binary classifier. Okay. So if you made it to the end of the video, good job, and I'll see you in the next one.